Alright, today we're going to do a couple of vector proofs. Just a couple to get you started. Okay. The first one, we're going to prove Pythagoras' theorem. Now we know Pythagoras' theorem when we have a right angled triangle, and we know side length A and side length B. We call this side length C, the hypotenuse. We know that C squared equals A squared plus B squared. Okay, so that's the identity we're trying to prove. Okay, and we're going to prove it using vectors. Okay, so we're going to, let's call this the origin, and we're going to call this vector vector A. So let's make that vector A, and this vector vector B. And we know that vector A and vector B are at right angles to each other. So we know that the dot product of A and B has to be 0. Okay, so we know that's the case already. Now we've got to try and get this identity out with these two vectors. Well, vector C, which way do we want vector C to go? Let's make it go this way. So we can say vector C. So we've got vector C, we'll start the proof, we'll start it down here. Vector C has to equal A, vector A. Oh no, that doesn't work. If we start here, we've got to go back along A, then up B. Okay, so we've got vector B minus A, or minus A plus B. Okay, so that's vector C. So let's do, to get C squared, we know if we do the dot product, C dot C, we'd get the magnitude of C squared. So that's a good place to start. So let's go with C dot C. That is B minus A dot with B minus A. Okay. Now let's distribute. So we get B dot B, B dot B. So that's minus A dot B minus another A dot B, and plus A dot A. Oops, A dot A. Okay, so the B dot B, that's the magnitude of B squared. Yeah, we've got minus 2A dot B plus the magnitude of A squared. Now, A dot B, because we're at right angles to each other, is 0. So we're only left with magnitude of B squared plus the magnitude of A squared, right? Has to equal C dot C, which is the magnitude of C squared. And we've got the proof. Okay. Now, what would happen if this wasn't a right angle? All right, and then we'd end up proving the cosine rule. We get A squared plus B squared minus 2 times A, or the magnitude of A times the magnitude of B, because of the angle between it, and you get the cosine rule. So it's 2 proofs in one. Yeah. Okay, let's do one more. Different one with a different tactic. Okay. Let's pretend, I don't know why I'm drawing this on an axis. We don't really need to, but that's okay. Let's pretend we've got a circle. That is a perfect circle, and has radius r. Okay, so we want to prove that if, okay, let's cross the diameter, and the angle inscribed on the inside of the circle here from the diameter, we get a right angle. So we're going to prove that this always has to be a right angle. Okay, if we've got a line, or if they come from the lines of a denominator, we always get a right angle triangle in the middle. Okay, so what do we know? We're going to have to use this circle stuff somehow. Okay, so let's try let's try defining a vector here from the center. Okay, we know it's has a radius of r. Yeah, we know that's the radius, but we're going to call it a. And this one's going to be a little bit different because I want to use the fact that the magnitude, from this distance to the point on the circle is also r. Yeah, this is always going to be the radius of the circle. So it doesn't matter where this point is, it's always going to be, the magnitude from the origin is going to be the radius. So I'm going to make a vector that goes up to that point there. I'm going to call it B. What's a rotten B? But we know we've got the magnitude of A has to equal the magnitude of B. Okay, they're not equal vectors because they're in opposite directions, but they are equal in magnitude. Okay, so we need to get this vector and this vector, and we want to show that they are at right angles. Okay, so to get this vector here, I'll do it down here. Okay, so should I do it in red? Let's do it in red. Okay, so this vector, we're going to go minus a plus b. Okay, so b minus a, that vector. And this vector, well, I've got to go a plus b because this vector here is also a. Yeah, that vector here, also a. Okay, so we've got this vector here being vector a plus vector b. Okay, so we just want to show that they're at right angles to each other. So let's do a dot product and see if the dot product equals 0. So we've got vector a plus vector b. We're going to dot that with vector b minus a. So what do we get here? We get ab, a dot b, expand that one out, minus a dot a, plus b dot b, minus a dot b. Okay, what have we got? We've got a dot b, which is a scalar number, minus a dot b, so they're gone. So now I just have the magnitude of, well, I've got the negative, I'll do it in blue. I've got minus the magnitude of a squared plus the magnitude of b squared. And since the magnitude of a is equal to the magnitude of b, so it's just, this is the magnitude of minus b squared plus b squared must equal 0 because they're the same thing. We're minusing one away from the other. So therefore, perpendicular, right angle. Right angle. Okay, that's it. There's 2 vector proofs to get you started. They take a bit more experience, I suppose, and practice, and getting to know getting to know different methods. I suppose the trick in this one was defining. We had to use the fact of the circle to define this radius b. It wasn't on the geometric picture to start with. But yeah, keep practicing.